In this video, we're going to be discussing the concept of measure of relative standing, which is basically how does a particular data point compare to the rest of the data set. And to do that, we're going to be taking advantage of two concepts we covered in previous videos. The first of which is the measure of central tendency, or how the data clumps or centers around a particular data point. And the second is the measure of variability, or how spread out is a particular data set. Now, the first measure of relative standing that we're going to discuss is called the pth percentile. And what the pth percentile is essentially for a particular data point, it's the percentage of the rest of the population, or the sample, that falls below that data point. So the most common place that you've probably seen this is in standardized tests. So for a standardized test, you generally get a score and a percentile in which you fall into. So the way that that works is if this is the distribution of a particular test grade, so we have, this is the outcome of a particular test, say the ACT or the SAT, and your test grade falls right here. The way that they calculate the pth percentile that you fall into is they find the percentage of the population that has a score less than the score that you received. So for our example, we're going to be using the weekly exercise time in minutes for 20 males from a particular university. So the first step in calculating the pth percentile for any particular data point is to first put the data points in order. So either ascending or descending, it doesn't make a difference, but we're going to need to sort the data in a particular order. So we're going to do that quickly off screen. So now that we have the data sorted, we can find the pth percentile for any particular data point. So for example, if we take 9.0 as the data point that we want to care about, we can find the percentile of the population that falls below that value. So to do that, we just need to now count the number of data points that fall below 9. So we have 1, 2, 3, 4, 5, 6, 7, 8 data points that fall before 9. So we have 8 divided by the total number of data points, or 20. If we do 8 divided by 20, we get 0.4, which we then multiply by 100 to get 40%. So we can now say that 9.0 falls in the 40th percentile, because 40% of the data falls below that 9.0 mark. So the most commonly used percentile that you've probably dealt with is the 50th percentile, or what we called before as the median. So we'll take a look at the median here. So for the median, we're going to find just the halfway point for our data. So if we're going to say our median, which is the 50th percentile, and to do that, since we have 20 data points, we again just average the two middle points. So we have our 28.5 and we have our 34.5. So we're going to average those two together. So we have 28.5 plus 34.5. And then we divide by 2. So if we add those two together, we get 63 over 2. And if we divide that, we get 31.5. So our median for our data set is 31.5 minutes. Now, we generally don't just deal with the 50th percentile when we're talking about percentiles and trying to describe our data. The two other percentiles that we generally deal with are called the lower quartile and the upper quartile. And when we're talking about the lower quartile and the upper quartile, we generally rename the median to be the middle quartile. So we're going to just erase median and make that as the middle quartile. And though there are only 3 data points that we're dealing with, the reason that they're called quartiles is because it breaks up our data into 4 evenly sized pieces. So to do that, our lower quartile needs to be the 25th percentile. So 25th percentile. And our upper quartile needs to be the 75th percentile. Now there are actually a couple of different ways that we can calculate the lower quartile and the upper quartile, but the one that we're going to use in this class is we're going to take our data set and we're going to find the median, and then we're going to find the median of the upper half and the median of the lower half. So to do that, since we have 20 data points, we find the median with the 2 middle points. So we're just going to take those 2 data points out of our data set. So we're going to say that these 2 are gone. And now we're just going to find the median for the top row of our data and the median for the bottom row of our data. So if we look at that, since we had 20 before and we took out 2, we have 18, which means we have 9 in each row. So if we look at the 5th data point, so 1, 2, 3, 4, 5, 0.0, and then we have 1, 2, 3, 4 above that as well. We can say that 0.0 is our lower 25th percentile, so we have 0.0. And for our top 75th percentile, we have 1, 2, 3, 4, and 5. So we have 78.0 as our upper quartile. So now if we look at this, it's breaking our data essentially into 4 evenly sized pieces. So we have from 0.0 down, from 0.0 up to the 31.5. We have from 31.5 up to our 78.0, and we have our 78.0 onward up to our 199.5. And this is how we're just going to describe our data using percentiles, or whatever we're going to refer to as quartiles. The second method that we're going to use to describe the relative standing of any particular data point is called the Z-score. And the Z-score is going to have the same formula essentially for both a sample and a population, where we're just changing out the way that we're describing the mean of that data. So we have the Z-score, or Z, is equal to the particular X value that we're trying to describe, minus the mean, so minus X bar, divided by the standard deviation, or S. And if we're dealing with the population, we would say that Z is equal to X minus mu, divided by the standard deviation of the population, or sigma. So what that is doing for us is it's telling us the number of standard deviations away from the mean that a particular data point resides. So we can then use some particular rules like the 68, 95, 99.7 rule, or Chebyshev's rule, to kind of describe what percentage or what fraction of our data lies between the mean and that particular data point. So to walk through a couple of basic examples for calculating the Z-score, we're going to need 2 pieces of information. And the first of which is the mean of the data, and we're going to treat this data set as a sample. So we're going to say the mean is X bar is equal to 47.6. And we're going to calculate out the standard deviation, or S, to be equal to 58.1. So now let's use this to calculate the Z-scores of a couple of different data points. So for our first example, we're just going to calculate the Z-score for 43.5. And to do that, we're going to say Z is equal to 43.5 minus the mean, or minus our X bar, which is 47.6. So 43.5 minus 47.6, and then we divide that by our standard deviation, which is that 58.1. So if we do that subtraction on the top of our fraction, we get 43.5 minus 47.6 is equal to negative 4.1, and then the bottom of the fraction stays the same at 58.1. So if we then do that division, we get negative 4.1 divided by 58.1, we get negative 0.071. So if we look at that data, we kind of try to get an intuitive feel of what that should look like. We see that 43.5 is just a little bit smaller relative to our standard deviation than the mean, which means that the data should be small in magnitude and will be negative for our Z-score, which is exactly what we're getting. So let's walk through a couple of other examples. So the next one we're going to do is we're going to calculate the Z-score for 0.0, which was our mode, or our most occurring element in our data set. And we're still going to subtract off the mean, so 0.0 minus 47.6, and divide it by our same standard deviation of 58.1. So if we do that subtraction, we get an obvious negative 47.6 on the top, and we get our same 58.1 on the bottom. So if we then do that division, we get negative 0.820 for our number of standard deviations away from our mean, or our Z-score for 0.0. And the last example we're going to do is we're going to be calculating the Z-score for 78. So we have 78 minus 47.6 divided by our standard deviation again of 58.1. So if we do that subtraction up top, we get 78 minus 47.6 is equal to 30.4 divided by our same 58.1. And for our z-score, we get 0.523. So that's how we calculate the z-score, which is our second measure of relative standing for any particular data point, which is basically telling us the number of standard deviations away from the mean that that particular data point resides.